Okay, so my shape is a square root of x as a base, and it's bounded from 0 to 4 on the x-axis. The specific shape is multiple isosceles right triangle cross sections, with the hypotenuse being the base of the solid. It looks like this. This is very complex. Yeah. A little bit uneven because I had different cardboard slices, but you know. Okay, so that's the introduction to my shape. How did I make my model? So my model is made of multiple cutouts of cardboard that are width of 0.2, and it's divided along the x-axis. There are about 20 of them. I glued them together from biggest to smallest, going from left to right, and then I pasted it onto the base. So my integral for this is capital F of x, being the antiderivative, equals 2x, or 2x to the power of 2/3 over 3, so I don't know if you can see that. Yeah. And then when you solve for that, it gives you 5.0396842, which is greater than my original volume calculated on my spreadsheet, which is right here. So my spreadsheet was the product of measuring each cross-section, the length, width, putting in the top function, and setting a certain amount of cross-sections. And that total, when I calculated the area, the side length, the width, the volume, and got the total volume, I got 1.612675606, which was significantly smaller than the total volume I got for my integral. I believe it was smaller because when you do it by hand, by measuring, you leave a lot of room for human error. My integral, I believe, is far more accurate because it gives you the closest approximation to 0 with the cross sections. What I mean by that is you get the closest distance of cross sections, the closest width of cross sections closest to 0, and I also believe that the human error was due to the differences in cardboard width and how my object was cut. And that was my original model. My second one is I did a pawn graph, which is right here. And I divided that up into 10 cross sections. Here are my equations. To find the actual spreadsheet, I did each of them. I calculated the integrals for each of them and bounded them by how I input them on Desmos, and I got a total of 1.3879131, which I believe was smaller than my original integral answer, and I believe it's smaller because, again, you're not getting the closest approximation to 0 as you can. The limitations, I believe, are not being able to find the closest approximation to 0, differences in cardboard, and whatnot.